I will design a 3-bit binary up counter using flip-flops. So if I think of an up counter, 3-bit one, the truth table will look like this. So let's say this is Q2, Q1 here, and then Q0. And let's say this is Y, just the output. So 0, 0, 0, 0, 0, 1, 0, 1, 0. Actually, we don't need an output. I'm just showing the counting. So 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So this is how it should go, a 3-bit binary up counter. Now we want to use flip-flops. If we recall the truth table of a JK flip-flops, it's JK, and then this is output Q. So if both are 0, it's no change. When 0, 1, this is 0. When 1, 0, this is 1. And when 1, 1, it toggles. So when these two are connected, when we look at these two inputs, that means when J and K are connected, it becomes a T flip-flop. And when these two, so when they are connected inversely, so when they are connected with an inverter here, it becomes a D flip-flop. We know that, and so this becomes the input of the D. And if they are just tied together, J and K inputs, so that's J, that's K, that's output Q, this is output here. When they're tied together, it becomes T. So that means that will have only two inputs, and that will be both J and K are the same input. That's the T flip-flop. So T flip-flop has a property where when the input is 1, there is no change, and when the input is 0, there is no change, and when the input is 1, the output changes, it toggles. So here we really didn't need this part. So here this is our, so let's draw 3 T flip-flops first. So these 3, and so let's say this one will be Q0, this one will be Q1, and this one will be Q2 outputs, and this will be T1, this will be T2. So we have to figure out what the inputs will be, and there's a clock here. So let's say the clock is connected with the first one, and of course, so we have a synchronous arrangement. All the 3 flip-flops have the same clock, so it's synchronous. So when we look at the truth table, we can see that Q0, which is our first flip-flop, the leftmost, it toggles the output of this one, or the value Q0 toggles with each clock. So it's always just changing. So what we can do, we can just write 1 here. So it will keep toggling with each of the input, with each of the clocks. Now if we look at Q1, which is this one, I will use a different color maybe. Q1, when this one, we can see that it is not changing, not changing here. So it's not changing just when the clock comes, but it is changing here. And when is it changing? If we look that when Q0 is 1, that means when Q0 is 1 and clock comes, this one changes. Let's see if that is happening all the time. So it's not changing here. Then again when Q0 is 1, this is changing. Here Q0 is 1, this is changing here. We are just looking at Q1, which is the middle column. So what we can do, if we connect this one here with the output of the first flip-flop, that is Q0, the least significant bit, the output of that is connected to the input of the middle flip-flop, that is Q1, then whenever it is a 1 here, this one will get a 1 here, the flip-flop input will be a 1 and the output will toggle. So that's happening. And when this output Q0 output is 0, this input T2 will get 0 as input, so there won't be any change. So if we with the first clock, this is all 0. Let's say we start with all 0. When the clock comes, this one becomes 1. What happens to the second flip-flop? It doesn't change because the input here is 0. So the output here is 0. So T2 will get 0 as the input when the clock comes. So it won't change. Sorry. But when the second clock comes, the output Q0 is 1. So the input T2, so this will be output Q0 and input T2. So when the second clock comes, this one will get a 1 here. So this output will toggle, which it's happening here. So this is how it will keep going on. Now if we think of the most significant bit, that is the leftmost column here, Q2, which is here, this one, we are trying to figure out what input will it have. It is getting the clock, but it should change, the output should change. When does it change? Let's look here. It's changing here, and that's the only point it's changing. Again, it's changing here when it has counted up to 111, so up to 7. So what is the significance of this one? The significance of this one is here both Q1 and Q0 are 1s. Both are 1. Similarly, here both are 1s. So when both of them, Q1 and Q0, when both are 1, only then the most significant bit should toggle, because that's only when, that's what happens actually when we are counting up binary. These two are 1, so then these two become 0 and this most significant bit becomes 1. Even if it were 4-bit, that's what it would happen. So if it was like this, then after this one would toggle. So from 7 to 8 would be like this. So similarly, this is happening here, it's just happening twice. So what is needed is, if we AND Q0 and Q1, and Q0 here and Q1, both are 1, only then output will be 1 when both are 1. And if we connect the output to here, to the input of T, actually I have said T2 here, should have said T1, T2, so this is T3. Yeah, it's not consistent because this is Q2, this is T3, but whatever. So yeah, I messed that up before, so I'm not changing anymore. So let's say this is T3. So T3 input will be Q0 and Q1 ANDed together. So only when both this output and this output both are 1, only then this input should be 1, so that the output here toggles. So that's how we can have an up counter, 3-bit up counter. It can be extended to 4, 5, just with the same logic. So if it were 4, then we had to AND for the fourth one, we had to AND this one, Q0, Q1 and Q3. We had to AND all those 3 together and then give that output to the input of the fourth one. So yeah.